Welcome to Talk Tensors. If you are tuning in, you are likely the kind of person who finds something strangely poetic about a well-optimized loss function, or maybe you just really miss the sound of a mechanical keyboard clacking away in a university lab.
Or, perhaps you are just exhausted from staring at those 2-column PDFs on a glowing rectangle and you want someone else to parse the Greek letters for you. Either way, we're glad you're here.
Today, we are not just covering a paper, we are covering the paper. In the history of machine learning, you get these moments, these inflection points, where the timeline just splits. There's a before and there's an after.
Yeah, people love to throw around the term paradigm shift. It gets overused for sure, but in this specific case, I think it's entirely justified. This is one of those times.
We are doing a deep dive into WaveNet, a generative model for raw audio. This is the paper that came out of DeepMind in late 2016.
And to really set the stage, you have to remember what the world sounded like in early 2016. Do you remember calling your bank's automated system or trying to get directions from a GPS?
Oh, vividly. Yeah, it was that stilted, chopped up cadence. 200 feet, turn, left. Each word was like its own little island of sound.
Right, it sounded like a robot. And not, a cool sci-fi robot with a personality. It sounded like a bored, slightly broken robot that was just reading a list of words. And then it felt like it happened almost overnight. The voices changed.
They really did.
They got breathy, they got rhythm, they started to have pauses and inflections. They started to sound human.
That transition, that leap, that was WaveNet.
That was WaveNet. This paper effectively solved the uncanny valley for speech synthesis. And the team that put it together, this was a DeepMind London production, was an absolute powerhouse. You have Aaron Vanden Oord, Sander Dillerman, Hege Zen, Karen Simonian, Oriel Vinyals, Alex Graves.
I mean, the author list reads like a Hall of Fame ballot for neural network research. These are the names behind some of the biggest breakthroughs of the last decade.
It really is a murderer's row of researchers.
So the mission for our deep dive today is to understand how they did it. Because the abstract makes this very bold, almost understated claim. It says they moved away from parametric approximations and started modeling raw waveforms.
Which, to someone not in the field, that probably sounds like a minor technical detail, just swapping out one method for another. But it's actually a completely different philosophy of what sound is and how to create it.
We need to unpack that. We need to really get into the weeds of why predicting raw audio was considered, almost impossible for so long.
And we have to get into the architecture, specifically these things they call dilated causal convolutions, which really do seem to be the magic wand here.
And we also need to talk about why on earth they treated sound, a continuous wave, as a classification problem. That's so counterintuitive to me.
It is. It's one of the weirdest and most brilliant parts of the paper.
All right, why are we classifying sound? But okay, before we get to the solution, we have to really, really understand the problem. So let's go back in time. Let's go to the dark ages of text-to-speech, or TTS. What exactly was happening inside that GPS unit in, say, 2010 that made it sound so strange?
So historically, you basically had two main schools of thought, two competing camps. In one corner, you had what's called concatenative synthesis.
Concatenate. Okay, that word sounds like concatenation, which, in programming means gluing strings of text together.
That is exactly what it is. It's the audio equivalent.
Yeah.
So imagine you want to build a voice for your system. First, you hire a voice actor.
Okay.
You put them in a professional recording booth for 40 hours, maybe more. You make them read thousands and thousands of sentences, covering as many phonetic combinations as you can think of. The quick brown fox jumps over the lazy dog. Please press 1 for billing, all of that.
And then you just chop all those recordings up.
Yeah. You chop them into tiny little units, sometimes words, sometimes syllables, but often you go even smaller, down to diphones. The transition between two phones, you get all these little audio snippets, you label them meticulously, and you throw them into a massive, massive database, gigabytes of it.
So when I type in hello world, the computer goes into this giant library, looks for a pre-recorded he, a low, a war, and a load sound, and then it just pastes them together.
Effectively, yes. A bit more sophisticated than that. Of course, there are algorithms to try and find the best joins, but that's the core idea, and that is precisely why it had that very specific recognizable sound. Some people call it the ransom note effect.
Huh. I like that, like a kidnapper cutting letters out of different magazines to make a threat. Each letter looks different.
Exactly. You might have the he sound that was recorded as part of a happy, upward inflecting sentence and the low sound that came from a flat, declarative sentence. When you glue them together, the pitch doesn't match up. The volume jumps.
The tone is all over the place.
And even worse, on a technical level, the phase of the audio wave doesn't line up at the seam, so you get these little audible clicks and pops. It's a dead giveaway that it's not a real human speaking continuously.
But the individual snippets themselves, they sounded perfectly human, right? I mean, because they were human recordings.
Yes, that was the big advantage. The texture, the richness, the grit of the human voice was there because it was just a recording, but it was profoundly inflexible.
What do you mean by that?
Well, what if you wanted that voice to sound angry or sad or excited? You couldn't. The emotions were baked into the original recordings. Your only option was to hire the voice actor again, bring them back into the booth, and have them re-record the entire 40-hour database while shouting.
Which is a logistical and financial nightmare.
A complete nightmare. You couldn't easily change the voice, the emotion, the pacing. You were stuck with what you recorded.
Okay, so that's the glue method. Concatenative.
Yeah.
What was the alternative? What was in the other corner?
The alternative was parametric synthesis. And this was sort of the more scientific or academic approach. The idea here was, instead of storing raw audio, you store a mathematical model of the human vocal tract.
This already sounds much cleaner, more elegant.
It is much cleaner. And it's also much, much smaller. You don't need gigabytes of audio files on your device. You just need this compact model that can predict a set of parameters.
Okay, what kind of parameters are we talking about here?
Things like the fundamental frequency, which is basically the pitch of the voice, you'll see it called F0, and then things called spectral envelopes, which describe the timbre or the tonal quality of the voice, what makes a violin sound different from a trumpet, even when they play the same note.
I see. So the model spits out these abstract numbers, not sound.
Exactly. It predicts a stream of these parameters, and then you feed that stream of numbers into a second piece of software called a vocoder.
The vocoder, okay, my mind immediately goes to Daft Punk or Kraftwerk when I hear that word.
It is the exact same family of technology. A vocoder's job is to take those abstract parameters, pitch, timbre, and try to synthesize a sound wave from scratch that matches them. But here's the fundamental problem. The vocoder is a liar.
A liar. How so?
It simplifies reality. To make the math tractable, especially back then, standard vocoders had to make these massive, sweeping assumptions about the nature of sound and speech.
Okay, like what?
Well, they assumed that speech could be modeled by a simple source filter model. You have a source of sound, like buzzing vocal cords, and a filter, which is your mouth and throat shaping that buzz. They assumed these were linear systems. They also assumed that the distribution of energy in the signal was Gaussian, a nice, neat, predictable bell curve.
But human speech isn't neat. It's messy. It's got pops and clicks and breaths and friction. It's chaotic.
Exactly. Real speech has phase coherence. It has nonlinear interactions. It has grit. The vocoder, with its simplifying assumptions, just smoothed all of that out. It took the rich, complex texture of the voice and turned it into a simple, robotic buzz. That's why parametric synthesis always sounded so muffled and robotic. It lacked the high-frequency crispness and complexity of reality.
So we were really stuck between a rock and a hard place.
Yeah.
You had concatenative, which sounded real but was glitchy and totally inflexible. And you had parametric, which was smooth and flexible, but sounded soulless and robotic.
That was the gap. That was the uncanny valley of speech. And for years, the entire field was focused on fixing parametric synthesis. The assumption was, we just need to predict better parameters. We need a slightly better vocoder. We just need to tweak the existing pipeline.
And then DeepMind comes along and it essentially says, what if the entire pipeline's the problem? Why are we messing around with parameters and vocoders at all? Why don't we just generate the sound?
It's that first principles thinking that DeepMind became famous for. They just stepped back from the problem and asked, what is audio fundamentally? And audio isn't a set of parameters. Audio is a wave. It is just a sequence of pressure values over time, a time series.
So they decided to model the raw waveform directly, sample by sample, the actual value, $6 a time, $2, the amplitude of the speaker cone at one specific moment in time.
It sounds so simple and direct when you say it like that, right? Just predict the wave. But I cannot overstate how computationally terrifying that idea was in 2016. It seemed completely out of reach.
Okay, put it in perspective for us. How does the scale of this problem compare to, say, text generation, which was a hot topic at the time?
Okay, so if I'm a big language model like an RNN or an LSTM back then, I might be generating one token or one word at a time. A typical sentence might be, 20 or 30 tokens long?
Right, a manageable sequence.
Now let's talk about audio. CD quality audio is sampled at 44.1 kilohertz. For speech, you can get away with a bit less, so let's say a standard of 16 kilohertz. That means 16,000 samples per second.
So to generate just 1 second of speech, the model has to make 16,000 separate predictions.
Yes. And not just any predictions, sequential predictions. Each one depends on all the ones that came before, because sound is continuous physics. The position of the speaker cone at sample 10,005 depends intimately on where it was at sample 10,004 and 10,003. If you get it even slightly wrong, you don't just get a typo like in text, you get a pop, you get static, you get white noise, the whole thing collapses.
And this is where the kings of sequence modeling, at the time recurrent neural networks or RNNs, they just completely choked on this problem, right?
They fell apart. RNNs and their more powerful cousins, LSTMs, were state-of-the-art for text and translation. But trying to enroll an LSTM for 16,000 steps, or even more to get context, is a computational nightmare. The gradients either explode or vanish to nothing, they take forever to train, they just aren't stable enough for sequences that are this incredibly long.
So DeepMind needed a new tool. They needed a way to look at a massive sequence of past data, understand the long-term context, and then make a very precise prediction for the very next step, but without using a recurrent network.
And so they looked over at their colleagues in the computer vision department, and they looked at a model called Pixel CNN.
Pixel CNN was an image generation model, if I remember correctly. It generated these cool, coherent images by generating them 1 pixel at a time.
Exactly. And they had this brilliant conceptual leap. They thought, well, what is an audio waveform? It's just a really, really wide image that's only 1 pixel tall.
That's a great way to think about it. And that brings us right into the methodology. This is the heart of the paper. They decided to use convolutional neural networks, or CNNs.
But there's a huge catch. A standard CNN, like the ones used for image recognition, like an AlexNet or VGG, it looks at the whole image at once. A convolution filter slides over the image, and to classify the pixel in the center, it looks at the pixels to the left, to the right, up, and down.
But in audio generation, you can't look to the right. The right is the future. That sound hasn't been generated yet. It hasn't happened.
Precisely. If your model looks at sample plus $1 in order to predict sample dollars, it's cheating. It's violating the fundamental laws of causality. The model would be useless for generation because at generation time, you don't have the future samples.
So they couldn't use a standard convolution. They had to use something they call causal convolutions.
Which is really just a fancy way of saying masked convolutions. You take a standard 1D convolution filter and you just zero out the half of it that looks into the future. So the prediction at time can only depend on inputs at time, $10, $2, and so on, into the past.
Okay, that makes sense. It solves the cheating problem. But doesn't that immediately introduce a massive blindness problem?
It does, and this is the central architectural conflict they had to solve in the paper. To generate realistic speech, you need context. You need a massive amount of context.
What do you mean by context here?
Well, think about prosody and intonation. If I start a sentence with a rising pitch, like I'm asking a question, are you going to the store? The way I say snore at the end is completely dependent on how I started the sentence several seconds earlier. That dependency spans maybe 2-3 seconds. At 16,000 samples per second, that's
tens of thousands of samples. So the model needs to somehow see 30,000 or 40,000 steps back in time to know how to correctly pronounce the word at the very end of the sentence?
Exactly. But a standard causal convolution with, say, a filter size of 3 only looks at the last 3 samples. To see back 40,000 samples, you would need to stack, thousands and thousands of layers. The network would be impossibly deep. It would be impossible to train, impossible to fit in memory.
It's like you're looking at the world through a tiny little straw when you desperately need a wide-angle lens to see the whole scene.
That is the perfect analogy. And this is where the stroke of genius comes in. This is the real aha moment of the paper. They didn't invent this technique, but they applied it brilliantly. They introduced dilated causal convolutions.
Dilated, like when your pupils get bigger at the optometrist.
It means expanding or spreading out. So imagine a standard filter. It looks at input 1, input 2, and input 3. A dilated filter with a dilation factor of 2 looks at input 1, skips input 2, and looks at input 3. It's a convolution with holes in it.
It has gaps. It's looking at every other sample.
Exactly. It widens its stance. And the real trick is in how they stack these layers. They don't just use one fixed dilation. They increase the dilation factor exponentially as you go up through the layers of the network.
Okay, walk me through that stack. What does it look like?
So imagine layer 1 at the very bottom. It has a dilation factor of 1. It's just a standard causal convolution. It looks at adjacent samples. It's responsible for capturing the very high frequency details, the buzz and texture of the sound.
Okay, the fine details.
Then layer 2 has a dilation factor of 2. It skips every other sample. Layer 3 has a dilation of 4. Layer 4 has a dilation of 8. They just keep doubling it. 1, 2, 4, 8, 16, 32. All the way up to a factor of, say, 512 near the top of the block.
Wait, hold on. If I have a filter at the top layer with a dilation of 512, isn't it just skipping 511 data points in between each input it looks at? Isn't it missing all that crucial information in the middle? That feels really sparse.
That is the common intuitive objection. It seems like it should fail, but you have to remember these are stacked. The layer with the big dilation of 512 isn't looking at the raw audio input. It's looking at the outputs of the layer below it, which had a dilation of 256. And that layer was looking at the output of the layer with dilation 128 and so on all the way down. So even though the top layer has these massive holes in its direct connection to the layer below, all the lower layers have already processed and summarized the information within those gaps.
I get it now. It's like a pyramid scheme for information. The bottom layer sees all the individual bricks. The layer above sees groups of bricks. The middle layer sees whole walls. And the top layer sees the entire building. Nothing is actually missed.
Exactly. This clever stacking allows the receptive field, which is the technical term for how much past audio the model can see, to grow exponentially with the depth of the network instead of just linearly.
So with the relatively shallow network, they mentioned stacks of 10 layers, repeated a few times, so maybe 30 or 40 layers in total. They can get a receptive field that sees back thousands and thousands of samples.
It was the perfect solution. It let them have their cake and eat it too. With one single unified architecture, they could model the tiny, high-frequency vibrations of the vocal cords that happen at the microsecond scale and the long-term intonational contour of an entire sentence that happens over seconds.
That is just incredibly elegant. It's one of those ideas that feels so obvious in retrospect.
It really is. It's a beautiful piece of neural architecture design.
Okay, so we've got the architecture. We have this telescope made of straws that can see far into the past. Now, the model has all this context, and it has to make a prediction. It has to decide what the value of the very next audio sample is going to be.
Right, the final output layers.
Now, normally, when we predict a number like the temperature tomorrow, or the price of a stock, or the amplitude of an audio wave, we treat it as a regression problem. We want the model to output a single continuous floating point number, like 0.743.
That is the standard intuitive approach. But again, DeepMind said no. They did something very strange. They treated audio generation as a classification problem.
Classification? Like deciding if an image is a cat versus a dog versus a bird.
Exactly like that. They broke the continuous range of possible audio amplitudes into a set of discrete categories, or bins, and then asked the model to just pick one.
Why? I don't get it. That seems so inefficient and wrong. Audio is continuous. Why would you force it into buckets?
It comes down to a subtle but profound point about the shape of probability distributions. When you do regression, and specifically when you use a common loss function like mean squared error, you are implicitly forcing your model to assume that the probability distribution of the correct answer is a Gaussian. A simple unimodal bell curve.
Meaning you're assuming there's one correct answer right in the middle, and any deviation from that is just random noise.
Right. But what if the true distribution isn't a simple bell curve? What if it's multimodal? Think about a sharp sound, like a snare drum hit. The waveform might need to go sharply up or roughly down, but it should definitely not stay in the middle. The true probability distribution might have two peaks, one at plus 0.8 and one at 0.8, with a valley in between.
And a Gaussian distribution can't model that. It would just average the two peaks out and predict the middle, which is 0.
And predicting the middle, predicting the average, is what results in that muddy, blurry, buzzy sound we hated in the old parametric models. By using a softmax output layer, which is standard for classification, the model can learn to predict any arbitrary shape of probability distribution it wants. It can say, there's a 40% chance the signal needs to jump to bin #250, and a 40% chance it needs to jump to bin #10, and a 0% chance it stays anywhere in the middle.
It preserves the sharpness. It preserves the hard edges in the sound.
It preserves the chaos and complexity of real-world audio. And that's what's needed for realism.
But wait a minute, let's talk numbers. Standard raw audio is usually stored as 16-bit integers. That means there are 2 to the power of 16. That's 65,536 possible values for each sample. A softmax layer with over 65,000 output classes is computationally massive. That would be way too slow to train.
It is. It's completely infeasible. So they knew they had to compress that range down, and they reached back into the history books and pulled out a technique that dates back to the 1970s telecommunication networks. It's called Oin-law companding.
Companding. Okay, that is a word I have not heard since my undergrad signal processing electives.
It's a portmanteau. It stands for compressing, expanding, and it's based on a fundamental quirk of human biology. Your ears are not linear microphones.
What do you mean by that?
Our perception of loudness is logarithmic, not linear. If you were sitting in a silent library and someone drops a pin, you hear it clearly. If you were at a loud rock concert and someone next to you drops a bowling ball, you might not even notice the difference in volume. We are incredibly sensitive to small changes in quiet sounds, but we're terrible at distinguishing small changes in loud sounds.
So a linear 16-bit audio representation wastes a ton of its data points, its precision, describing the tiny differences between really, really loud and really, really, really loud, which our ears can't even perceive.
Precisely. Oin-law is a nonlinear transformation. It's a function that squashes the signal. It effectively allocates more of the available bins or categories to the quiet parts of the audio signal, where our ears are most sensitive, and it uses fewer, more spread out bins for the loud parts.
It optimizes the data representation for the human ear, not for the raw physics.
You've got it. This clever transformation allowed them to quantize the 16-bit audio signal down to just 256 discrete categories.
256. That's just 8-bit audio. Shouldn't that sound like a fuzzy, low-quality old Nintendo game?
You'd think so. If it were a linear 8-bit quantization, it would sound terrible. But because of the logarithmic spacing of those 256 Oin-law bins, it sounds almost indistinguishable from the original 16-bit audio to the human ear. It was a massive breakthrough for making this approach computationally possible.
So they turned an impossible 65,000-way classification problem into a very manageable 256-way classification problem, all without a perceptible loss in audio quality. That's brilliant.
It's a fantastic example of combining old-school signal processing with modern deep learning.
There's one more piece of the architecture puzzle I want to touch on before we get to the results. The paper mentions they use something called gated activation units, and specifically did not use RayLU, the rectified linear unit.
Yeah, RayLU is, the bread and butter of most deep learning vision models. It's so simple and effective. If the number coming in is negative, make it 0. If it's positive, just keep it. But for audio, they found it just wasn't expressive enough.
Why not? What's the problem with it?
They borrowed a more complex idea from the LSTM and GRU playbook. They used a gated unit. The equation in the paper is SABU tan sigma W gate X.
Okay, let's decode that for a second. We have a tan function and a sigmoid function, and they're multiplied together.
Right. Think of the tan part as the content, or the filter. Tan is a great activation for audio because it's symmetric around 0. It handles the positive and negative swings of a sound wave equally well. Then, think of the sigmoid part as the gate. A sigmoid function squishes its input to a number between 0 and 1. It acts like a valve or a faucet.
So the gate, which is its own little neural network, learns to decide how much of the content from the tan part should be allowed to pass through to the next layer.
Exactly. It gives the network a dynamic mechanism to selectively ignore certain information or to pass other information through completely unchanged. This is absolutely crucial for modeling the very long-term dependencies in audio. It helps to avoid the vanishing gradient problem because the valve can just learn to stay wide open, creating a sort of information superhighway for important signals to flow many layers deep through the network without getting diminished.
Okay, so we have the dilated convolutions to see the past. We have the on-law quantization to simplify the output. We have these gated activations to manage the information flow. But if I just turn this machine on now, it's just going to babble, right? It doesn't know what it's supposed to be saying.
Right. An unconditioned WaveNet is a generative babbler. It will make sounds that have the texture and rhythm of human speech. It will learn to pause, to breathe, to have intonation, but there will be no actual words. It'll sound like someone speaking a made-up language.
So how do we steer it? How do we get it to say the words, "Welcome to Talk Tensors"?
Conditioning. This is how you control the output. The paper describes 2 main types: global and local conditioning.
Okay.
Global conditioning is like a master switch for the whole generation process. The best example is speaker identity. You create a one-hot vector or an embedding for each speaker in your training set, and you feed that single unchanging vector into every single layer of the network. It's a constant bias that says, be speaker A for this entire clip.
It effectively nudges the entire probability distribution at every time step to favor the vocal texture, the pitch range, the unique qualities of that specific person.
Right. But for text-to-speech, that's not enough. You also need local conditioning. You need to provide the specific text. But here we run into another one of those resolution mismatch problems.
Let me guess. The text information is much slower than the audio information.
You got it. Your text might be represented as a sequence of phones. A single phone might last for, say, 100 milliseconds. But in that same 100 milliseconds, the audio model is running at 16,000 steps per second. So it needs to make 1,600 predictions.
So you have one single instruction, like make an A sound.
Yeah.
And you need to somehow stretch that one instruction out so it guides the model for all 1,600 of those tiny audio samples.
Exactly. You need to upsample the conditioning signal. To do this, they used a technique called transposed convolutions, sometimes called deconvolution. It's essentially a learnable upsampling layer that takes the slow sequence of linguistic features and stretches it out to match the high resolution of the audio.
It's like taking a small rubber band with the foams written on it and carefully stretching it out to fit perfectly along a long yardstick representing the audio samples.
That's a great way to put it. This ensures that the model knows at every single microsecond which foam it is currently supposed to be in the middle of generating.
All right. They built the machine, this incredibly complex, elegant machine. They trained it on Google's massive compute clusters. The big question is, did it actually work?
It didn't just work. It broke the scale. It completely reset expectations for the entire field.
So how do we measure that?
In speech synthesis, the gold standard is a subjective metric called a MOS, a mean opinion score. It's very simple. You generate audio clips, you play them to a group of human listeners, and you ask them to rate the naturalness on a scale of 1 to 5.
Where 5 is perfect, indistinguishable from a real human speaking.
Right. Now, to give you some context for the numbers, real, actual human speech recorded in a studio usually rates somewhere between a 4.5 and a 4.6. It's never a perfect 5.0 because, people are critical listeners.
Okay, so that's the ceiling. What were the baselines?
The best parametric systems at the time, the robotic-sounding ones, were scoring around a 3.7. The best concatenative systems, the glitchy, glued-together ones, were a bit better, maybe a 3.8 or a 3.9.
So there was this persistent, stubborn gap of about 0.6 or 0.7 MOS points between the best AI systems and real human speech.
A huge gap. And then WaveNet came out. In their experiments, it scored a 4.21 on English and a 4.08 on Mandarin Chinese.
Whoa. So it didn't just inch forward. That is a quantum leap.
It cut the gap between the previous state-of-the-art and human-level performance by more than 50% in a single paper. In the world of MOS scores, where research groups fight and claw for a 0.1 point improvement over years, a jump of 0.3 or 0.4 is just it's unheard of. It was a mic drop moment.
And if you're listening, you really have to go and find the original samples from the DeepMind blog post for this paper. The difference isn't just a number, it's visceral. It's the difference between hearing a recording of a person and feeling like there's a person in the room with you.
The paper makes a few specific notes about what made it better. They said the buzziness of the parametric models was completely gone. The silences between words were clean. And crucially, the model learned to create breath sounds.
The breath.
Yes.
Yeah, I remember hearing that.
The model learned on its own that humans need to breathe. So it would automatically insert these subtle, realistic inhales before it generated a long sentence. It was never explicitly told to do that. It just inferred from the data that the probability distribution of a gasp of air sound is highly correlated with the probability distribution of the start of a new sentence.
That's incredible. That brings us to the multi-speaker experiment, which is the one that really, really blew my mind when I read this. They trained it on a data set called VCTK, which had 109 different speakers.
Right. And for this particular experiment, they didn't give the model any text to read. They only gave it speaker IDs. It was pure, unconditioned generation, just steered by the speaker identity.
So the model was just hallucinating speech in 109 completely different voices.
Yes. And because it wasn't constrained by any text, it just babbled. It made up words. It would say things that sounded like sentences, like the morkin of the splesh is on the fram. It had grammar and cadence, but no meaning.
Like a possessed toddler speaking in tongues.
Exactly. But the voices were perfect.
Yeah.
You could clearly distinguish all 109 different identities. And here's the truly wild part. It didn't just learn the voices. It learned the acoustics of their recording environments.
What do you mean?
Some of the speakers in that VCTK dataset were recorded in professional soundproof studios. Others were recorded in, slightly echoey university offices. Some of them clearly used low-quality microphones with a bit of hiss. WaveNet learned the room tone and the microphone quality as an integral part of the speaker ID.
So if you asked for speaker 42, you didn't just get speaker 42's voice, you also got the faint echo of speaker 42's room and the specific hiss of their microphone.
That's right. It implies that WaveNet isn't just learning a model of speech. It's learning a holistic physics simulation of the entire recording environment. It's modeling the microphone diaphragm, the sound waves bouncing off the walls, the air in the room, and the person's vocal cords all at once from raw data.
That's a much deeper level of understanding than I would have expected. They also, just for kicks, threw music at it, right? Just to see what would happen.
They did. They trained it on the Magnetagatune data set, which has all sorts of music, and a specific YouTube piano data set.
And what were the results there?
The results were hauntingly beautiful, but also kind of funny and ultimately a failure. In terms of timbre, the specific texture of the sound, it was perfect. When it generated a piano sound, it sounded like a real Steinway grand piano. You could hear the attack of the hammer on the string, the sympathetic resonance, the decay of the note. It was physically perfect.
Look, there's a but.
But musically, it was a complete mess. We talked about the receptive field being pretty long, maybe a few seconds. Well, music has structure that spans minutes. You have a verse, a chorus, a bridge, a repeating motif.
Right, long-term structure.
WaveNet's receptive field wasn't long enough for that. It would start playing a beautiful, coherent classical piano piece. Then, 3 or 4 seconds later, it would seamlessly and confidently drift into a completely unrelated jazz chord progression. Then that would devolve into a tonal chaos. Then it might sound like a different instrument for a moment.
It's like a brilliant concert pianist who has severe short-term memory loss. Every 3 seconds, they completely forget what song they were playing. But they're so good, they just keep improvising something plausible.
That's the perfect description. It really highlighted the limitations of that receptive field. It was great for the local structure of speech, like sentences, but it wasn't nearly enough for the global structure of a musical composition.
Before we move on to the limitations and legacy, we have to mention the discriminative task.
Yeah.
They didn't just use WaveNet to generate things, they flipped it on its head.
Right. The thinking is, if you have a model that understands the probability of raw audio so deeply that it can create it, then surely it can also be used to classify or recognize audio.
So they adapted the architecture.
They did. They modified it to perform phone recognition on the classic TiMide dataset, and they achieved a phoneme error rate of 18.8%.
Which at the time was the best score ever obtained by a model that was trained directly on raw audio samples.
It was a huge proof of concept. It proved that this architecture was robust in general. It wasn't just some one-trick pony for generation. The dilated causal convolution stack is a fundamental and powerful way to process any kind of high-resolution time series data.
Okay, so it sounds perfect. It generates stunningly human-quality speech. It can clone voices. It understands acoustics. It can even do speech recognition. Why didn't Google immediately roll this out to every Android phone and Google Home device the next day? There has to be a skeleton in the closet here.
There is a very, very large skeleton in the closet, and that skeleton is speech, or rather the complete lack of it. Remember how we established that audio generation with this model is sequential. It has to generate sample 1, then feed that back in as input to generate sample 2, then feed that back in to generate sample 3.
Right, autoregressive.
And remember how deep this network is? Maybe 30, 40 layers of very heavy convolution operations?
Oh no, I see where this is going.
To generate 1 single second of audio, just 1 second, you have to perform a full forward pass through the entire massive neural network, 16,000 times.
On 2016 era hardware.
On a top-of-the-line GPU in 2016, it took several minutes, in some cases, depending on the setup, maybe even an hour to generate a few seconds of audio. It was excruciatingly, painfully slow. It was a beautiful, perfect, but completely unusable research artifact for any kind of real-time application.
You can't have a conversation with your Google Assistant if it takes 45 minutes to reply, I found 3 restaurants near you.
Exactly. So the immediate legacy of this paper was this fascinating paradox. On one hand, everyone in the field knew that the uncanny valley problem was, in principle, solved. We now knew how to generate perfect human speech. But on the other hand, we couldn't actually afford to do it in practice.
So what happened? Because obviously my phone talks to me in real time now, and it sounds pretty good.
This paper triggered a gold rush. It kicked off a whole subfield of research focused on one thing. How do we get WaveNet level quality but fast? How do we make these neural vocoders practical?
So people started trying to distill it.
Exactly. The very next wave of research produced models like Parallel WaveNet, which used a clever technique called probability density distillation. The idea was to train the big, slow WaveNet first, and then use it as a teacher to train a much smaller, faster, non-autoregressive student network to mimic its outputs.
And that led to other approaches too, right?
It opened the floodgates. It led to flow-based generative models like WaveGlow. It led to GAN-based vocoders like HiFi-GAN and HiFi-GAN, which are still widely used today. All of these faster models were chasing the quality benchmark that WaveNet had established.
But they all trace their lineage back to this one seminal moment.
They absolutely do. WaveNet set the quality ceiling. It proved for the first time that deep neural networks could directly handle the messy, high-frequency world of raw audio waveforms. Every high-quality AI voice you hear today, from your smart assistant to the voices from 11 Labs to the voice mode in ChatGPT, is a direct descendant of the core concepts proven in this paper.
It was the moment the machine learned to dream in sound.
That's a beautiful way to put it. It really was.
Okay. We have analyzed the past. We have dissected the present. Now, as we always do, it's time to look to a weird and speculative future.
Here we go.
It is time for our Novel Notions segment.
This is the part of the deep dive where we take the rigorous peer-reviewed science we just discussed, we throw away all the safety manuals, and we propose some new research ideas that are, let's say, theoretical, maybe plausible, but mostly just for fun.
And of course, our standard disclaimer. These ideas are for entertainment purposes only. If you go out and try to build these and you accidentally create a sentient sound wave that learns the resonant frequency of the universe and takes over the internet, Talk Tensors is not liable.
Fair enough. All right, what do you have for me this time?
Okay, idea number one. I'm calling it the Acoustic Forensic Reconstruction Engine.
That sounds like something straight out of a CSI-style TV show.
Stick with me here. We established earlier that WaveNet doesn't just learn the voice. It learns the acoustics of the environment as part of its conditioning. In that multi-speaker experiment, it learned echoey room, or bad mic, just as well as it learned male voice or female voice.
Right. It models the entire signal triple environment and all.
So the standard approach to audio cleanup right now is denoising. We use an AI to try to subtract the noise. We try to filter out the background music in a bar to isolate the voice.
Okay.
But what if we do the complete opposite? What if, instead of cleaning the signal, we resynthesize the voice from scratch in a new, clean environment?
Go on. I'm listening.
Imagine we train a massive WaveNet model, but not on a data set of speakers. We train it on a data set of environments. We have a global condition label for cathedral, another one for subway car, one for inside a car on the highway, and most importantly, we have a label for anechoic chamber, a perfectly silent, echo-free recording studio.
Okay, so you have a model that can generate sound with the acoustic properties of any of these locations.
Now, you give me a terrible piece of audio, a corrupted file, a spy recording made in a windy tunnel with a hidden microphone. You can barely make out the words. I don't even try to filter out the wind.
What do?
I run a very robust speech-to-text model on it, or maybe just a foam recognizer, to extract the content. I get the sequence of linguistic units. At the same time, I run a pitch tracker to extract the F0 contour, the melody of the speech.
So you're extracting the blueprint of the speech, what was said and how it was said, but you're throwing away the noisy waveform itself.
Exactly. Then I take that blueprint, the foams and the pitch contour, and I feed it as local conditioning into my environment-trained WaveNet, and I set the global conditioning vector to anechoic chamber. I ask the model to hallucinate what that exact speech would have sounded like if it had been recorded in a perfect professional studio.
That's fascinating. You are not cleaning the audio at all. You are completely regenerating it based on its core components.
It's the audio version of the ship of Theseus. If I replace every single sample of the audio with a new AI-generated sample, is it still the same recording? No. But it preserves the original speaker's intent and performance, and it sounds perfect.
The obvious danger, of course, is hallucination in that first step. The speech-to-text model might get a word wrong. It might change. We need to disarm the bomb
A very real risk.
Yeah.
High stakes. But for non-critical applications, Imagine taking a scratchy, barely audible wax cylinder recording of a historical figure from 1890, and instead of just filtering out the scratches, you resynthesize their voice with the full fidelity of a modern podcast. You're not just filtering noise, you are dreaming the voice that was buried underneath it.
It's generative restoration. I really like it. It leverages the model's probabilistic nature as a feature, not a bug.
All right, your turn. What have you got?
Okay, my idea leans more into the compression aspect we touched on briefly. The fundamental insight from information theory, from Shannon entropy, is that if a model is a really good predictor, it's also, by definition, a really good compressor.
Right, because if I can perfectly predict what you're going to say next, you don't actually need to waste the bandwidth to say it.
Precisely. So I call this idea the deep space codec, or maybe more generally, the 100x generative codec.
Okay, I'm intrigued.
Imagine we are finally sending astronauts on a long journey, say to Mars. Bandwidth between Earth and Mars is incredibly precious and has high latency. You can't just stream HD video or high-fidelity audio back and forth. It's way too much data.
Right, it would be a trickle.
But what if the astronaut on Mars and mission control back in Houston both have a perfect, identical copy of the same pre-trained WaveNet model? And this model has been trained extensively on that specific astronaut's voice.
I see where this is going. A personalized model.
On Mars, the astronaut speaks into their microphone, "Houston, we have a problem." The computer in their helmet doesn't transmit the raw audio waveform. Instead, it does exactly what you just described. It extracts the text, the phones, and the pitch contour, the F0. That's a tiny, tiny amount of data. That's basically just a text file with some metadata. A few kilobits per second at most.
You're transmitting the script and the sheet music, not the actual performance.
You're transmitting the script and the melody, yes.
Yeah.
Maybe you also transmit the random seed number that was used for the stochastic part of the generation, just to ensure the resulting waveform is identical on both ends. You beam that tiny little data packet to Earth.
Which takes minutes to arrive.
And when it arrives, the computer at mission control doesn't play a recording. It plugs those parameters, the text, the pitch, the seed, into its local copy of the astronaut's personalized WaveNet. And the WaveNet hallucinates the audio in real time.
So mission control hears the astronaut's voice perfectly. They hear the breath. They hear the stress or the fear in their voice because it was captured in the pitch contour. But that actual sound wave never traveled through the vacuum of space.
Exactly. It was drummed up locally by the AI on Earth. The information content was transmitted, but the waveform was reconstructed.
You're effectively bypassing the Nyquist-Shannon sampling theorem for communication. You're not transmitting samples of a wave. You're transmitting a compressed representation of the intent to create a wave.
It's telepresence via generative hallucination. You could theoretically have crystal clear 48 kilohertz stereo audio over a connection that's as slow as a 1990s dial-up modem.
Or think about applications in video games. A game with thousands of lines of dialogue doesn't need to store 50 gigabytes of voiceover files on your hard drive. It just needs to store the text files and a trained WaveNet model for each character, and it generates the dialogue on the fly as you play.
And that's not even science fiction anymore. That future is happening right now thanks to these technologies.
It is wild to think that this incredibly dense, mathematical, slow as molasses paper from 2016 is the direct ancestor, the foundational spark for why that future is even possible.
It really was the spark that lit the fire.
Well, on that mind-bending note, I think it's time for us to wrap up. To summarize this deep dive, WaveNet marked the pivotal moment when machines stopped trying to imitate sound and truly learned how to generate the raw texture of it from first principles.
Yeah, it showed that with enough data, a clever architecture like dilated convolutions, and a probabilistic mindset, deep learning could finally conquer the high-frequency chaos of the real analog world.
It moved us from gluing recorded sounds together to dreaming sound, one sample at a time.
And we're all still listening to the results of that dream today.
Thanks for listening to Talk Tensors. As always, you can find a link to the original paper in the show notes if you want to brave the math yourself. We'll see you on the next deep dive.
Keep learning.